So I should start. Okay, thank you very much, Nikita. Well, I would really have preferred to come physically once to see you, but okay, also good this way. So Nikita asked me to, hello everybody, to say something elementary. And I think Lagrangian manifolds are something really good to be elementary. It's not so, in a way you understand them by examples, I think. Like many things in symplectic geometry, you only understand by examples because it's somewhat hard to feel what symplectic means. When you come from Kähler, things are much easier because you have distances, and in symplectic, it works somehow only through examples and the tools themselves. The tools are somewhat more geometric, like J-homomorphic curves, than the objects you study themselves. So my idea is to give you many examples and then ask certain questions, right? And you should immediately ask and protest and so on. Good. And well, it will be very introductory, but still there are some results, and they are mostly by two young people, Shoei Brendel and Juntae Kim, and also Fran Jura Chekhanov, and partly myself. Great. Okay, so I will, of course, start with definition. So I always take a symplectic manifold in the background. Usually it's closed, but maybe not. And I think you know what it is. It's a closed, non-degenerate two-form. But if you don't know that, it's also not important. Examples will be such that you see everything. And the Lagrangian therein is a submanifold. I should have maybe said that it is maximally, so it is a half-dimensional submanifold on which the symplectic form vanishes. It is the maximum dimension where this can happen. And these objects are somehow interesting from several perspectives. And I try to make that clear by examples. And then I will focus on one aspect of Lagrangian reality, which is just one among many, but I made this choice because there is some new things going on there. And then I will discuss how to distinguish Lagrangian submanifolds, and also to see whether they can be real or not. It's just a certain choice of topic that can still be treated in an elementary way. Okay, so let's start with examples. So the far most important example is a curve in the plane. It was ridiculous because there is nothing to check. Any curve is Lagrangian for the standard form, and usually I take them embedded and simply closed so that it is really compact. And this is a very important example because you can take products and then already get really important examples. Good, not so interesting, but important. And then the second example is also kind of very easy. You take a smooth manifold Q and take the cotangent bundle with the usual symplectic form. So this is, of course, why they are important in physics. So when you don't like this T star Q thing, probably you anyway like it, but you can just take a coordinate patch in Q and all the fibers over it, and when the coordinate patch is simply connected, this is really the same as R4 or R2N in general. So this is the same example as before. Standard, when you take the R2 and take it n times in product, you get really the same as here. So, but probably you anyway accept it. So when you take a smooth manifold Q and the cotangent bundle over it, then there are several very important Lagrangian submanifolds there. So first, every fiber is Lagrangian. Well, topologically, this is not interesting. It's an Rn, and it's obviously Lagrangian because, well, dq dp can only eat dp's, so there is nothing to evaluate non-zero, right? So then, kind of orthogonal to it, there is the zero section. It's also Lagrangian, and more generally, any section of a closed one form is Lagrangian. And actually a section is Lagrangian if and only if the one form is closed. So there is already a kind of an interplay between the notion of Lagrangian in symplectic and the starting point to form homology classes, right? Good. So these examples are actually very important, even though very simple.
I'm sorry, so Lionel asked in the chat that the left part of your slides cannot be seen. It's strange because I see them.
you see them.
Yes,
So
but
what shall I
Lionel
do?
does not see them.
Okay, maybe it's just my screen. I don't know. It's not center. Okay, I'm not the only one.
You are not
If
the
you
only
go,
one. Should I when I make it? Do you now see?
for example, this formula on top. Now I see most. Yeah, it's.
Maybe
I don't see a full
view.
screen actually. I just see a part of the screen, so I don't know if it's just me or. Wait. Now, okay. Now I see everything. Okay. Okay. So
now still.
Now, yeah, it's fixed. Maybe you can even zoom in.
Okay. Good. Good. Go test again if it doesn't work.
Sorry for interrupting.
Great. Great. Okay. Good. So why are they important? You see, when you look, for instance, in geodesics, you look from geodesic from Q to P. When you address this problem in a Hamiltonian fashion, you look at certain curves from cotangent fibers to cotangent fibers. So this is then you form a loop space with a Lagrangian boundary condition. And then when you go on, you can do more, not only Morse homology, but really Floer homology for these non-compact submanifolds T, Q star Q. So even though they look totally trivial, they play in the modern theory a very important role. They are also in the upgraded Floer homology in Fukaya category. The main submanifolds are spheres and fibers. So these fibers are very important, even though at first they look very harmless. So they are important in dynamics, and these alpha of Q, these sections, they are also important. So the starting point of Floer's construction usually really came from there. For instance, there is Kroll theorem that well, also by Sikurov and Laudenbach, that when you take the zero section and you apply to it any Hamiltonian diffeomorphism, then you cannot disjoin, even if the Euler characteristic vanishes. It cannot be done. There must be a Lagrangian intersection. And this led really to the modern development. This is just about this somewhat harmless section, zero section Q, right? And when you study magnetic fields, then these alpha of Q are also very important. So this is kind of good to have in mind, even though there is no interest in topology. So then another reason why Lagrangians are important is this Weinstein saying that everything is Lagrangian. So we symplectic topologists always think that it is meant in the way I will say now, but he probably meant it from the point of view of quantization. So I don't understand that. But it is true that most concepts and important things in symplectic geometry and Hamiltonian mechanics can somehow be reformulated in a Lagrangian way. And I will just now make one classical example. That was also key for Floer's introduction of Lagrangian Floer homology. It's like this: you take a symplectic manifold, M omega, and then you just form the product and you switch one form to minus. And then, of course, the diagonal therein is Lagrangian, right? It's a copy of M diagonally therein. But actually, for any symplectomorphism phi, the graph is Lagrangian. So being Lagrangian, I think it's actually, for phi, it's equivalent to being phi symplectic, right? So you have this graph, gamma phi, and so you have many Lagrangians. There are kind of deformations of the diagonal. And when you look at these graphs, you can sometimes view certain dynamical questions in a much more geometric way. So here is one of them. There are many other examples. So you clearly see that a point in X is a fixed point of the mapping phi, if and only if the graph of phi, gamma phi, intersects the graph of the identity in exactly the point XX. Yeah, because phi of X is XX, if and only if phi of X is X. So now when you take phi not to be just a symplectomorphism, but a Hamiltonian diffeomorphism of a Hamiltonian that is time one periodic, or if you want, autonomous, you choose. Then finding one periodic orbits of a Hamiltonian system on M is the same thing as finding Lagrangian intersection points of these two Lagrangian submanifolds, which is a much more geometric and topological problem, and which is addressed by Floer by his Lagrangian Floer homology, right? So you can very often go forth and back between dynamical questions on M and topological geometric questions on the product, right? So this is one kind of good motivation. When you want to geometrize dynamics, then Lagrangian pop up immediately. Great. So next one. So from very classical mechanics, of course, Lagrangian tori come up all the time. When you take, maybe I now assume the manifold to be compact, to have to say a bit less. And now you assume that you are in an integral system. It means that you have n smooth functions on your manifold, and they are in involution. So this strange bracket means Poisson bracket. And well, of course, you can write things in coordinates like in school, but you can also say, it means that the symplectic form of the two Hamiltonian vector fields given by Fi and Fj is everywhere 0. Well, you also want probably to have some results that the gradients are almost everywhere linearly independent. And then you can reduce the system, right? And if you have really n such functions, then when you are in Rn a regular value of this composed function, you take all the Fi, you form from it a function from the manifold to Rn. So then if this value C is a regular value, then the preimage is a Lagrangian torus, which follows, well, that is Lagrangian follows immediately from this Poisson bracket thing. And that it's a torus follows from the, well, because the flows commute and because I have assumed that the manifold is compact. And not only, well, because you have a regular value, of course, close by, you're also a regular value. So a whole neighborhood is now foliated by tori, right? You have a little n ball in this Rn so that the whole neighborhood is foliated by Lagrangian tori. So this is the topological statement of Arnold-Liouville theorem. But this is, of course, not very important. But what is much deeper is that the dynamics on this neighborhood is completely understood. On every such torus, the flow is Kronecker, it's linear. And the slope of the lines is, of course, dependent on the value C. But once you know this slope, you know everything. So to fix idea, you just assume that one of these Fi is really the Hamiltonian you're interested in, like the total energy. And then you have like other ones, many other ones, enough, n-1. And then the flow of H that you want to know is very simple, right? It's either if at a given C, the slope is rational, then everything closes up. And if not, it's a totally non-closing up irrational flow. So these systems are, of course, they were already studied by Liouville and Jacobi, but then, thanks to COM theory, they are also important when you perturb the system. When to be really completely integrable is very rare, but most systems are, well, many important systems, like in three-body problem and so on, they are perturbations thereof. And then, thanks to Kolmogorov-Arnold-Moser theorem, you still have many, many tori. You don't have a foliation by tori, but you have something like a contour set of tori, and if these, under certain conditions about these slopes, you have still a positive and sometimes very large measure of tori that you can use for several things. Sometimes it gives you stability in small dimensions and so on. So they appear, so Lagrangian tori appear everywhere in mechanics. Good. So now I exaggerate this. I take as before such an Arnold-Liouville situation, but now I even assume that all these tori are, well, everything fits up extremely nicely, everything closes up, and the whole thing is, what I want to assume is that there is a moment map. The whole dynamics is given by a Tn action by Hamiltonian diffeomorphisms. It's a subcase of the previous one. Of course, this is now a kind of topology geometry. This in dynamics appears rarely. But this is nice because it gives a link to toric geometry, and it gives you many manifolds, and with all these more algebraic tools you have to study them, right? So I will not define formally what a moment map is. You should just think of a sphere, just one of the left one, say, and the height function. Just the z coordinate is your Hamiltonian, and then everything turns with the same period. So the Hamiltonian flow is then just a rotation. And when you take products, then you have what I say here. So the preimage of the moment map is then the preimage of such a red point is of course, the Lagrangian torus. And in the picture, it's just these torus you see, the red circle crossed the other red circle. And the green disk plays a role only later. Good. So this is, of course, dynamically really very special, but can relations to many other mathematics. So toric systems, right? Questions? Good. So then another extremely easy example. So I had these loops before in the plane, and now I take products thereof. So I have now such a product torus in R2n, product of circles. And when I write this, I mean really S1 enclosing area A1 in 1R2, and then the same with A2 and so on. And these things are classified in Cn. And I will not write down the classification. It's actually not so easy. So for the smallest one, for instance, is an invariant. And then there are other relations. So of course, when I say classified, I did not even say up to what. And here in symplectic geometry, you should be really careful. When you look at Lagrangian submanifolds, you essentially have three types of classifications you want to address. So one of them is that you just have two Lagrangians, L0 and L1, and you connect them by Lagrangian isotopy. It means that you have a smooth family LT of Lagrangians starting from one to the other. They may, when you have two circles of any size, of course, you can connect them in a plane. So this is the weakest relation you could ask for. So the second one is that you have a global symplectomorphism of the ambient space that maps one to the other. So for instance, for circles in the plane, the circles must now enclose the same area, right? So this is stricter. And the strictest one is that you move one to the other by Hamiltonian isotopy. So this again is a different relation. For instance, if you take a cylinder, just R cross S1, then Hamiltonianly you cannot move up a circle, but symplectically you can move it up. So these three relations are different, and when you say classify, you should carefully say what you mean. So this classification of products of circles in R2n, it turns out to be the same in the Hamiltonian and the symplectic case, and it's kind of nice. And of course, when you only look at Lagrangian classification, they are all the same, of course, because you can just scale as you like. Great. So now, among Lagrangian submanifolds, there are certain notions. For instance, monotone or real or exact, and they play important roles for different questions. And I will only address two. One of them because otherwise I cannot make statements, namely monotone, and later because I want to say something about it, namely real. So monotone is a really important notion, roughly because they are the most interesting ones, and also because for them, the tools like holomorphic curves and Floer homology play far the best. So the formal definition, maybe I first say what it means for such a product in R2n. It means that all the circles have the same size. And in general, it means the following. When you have a Lagrangian submanifold, then you have two important homomorphisms from the second relative homotopy groups, one to the real and one to the reals and one to the integers. The first one, sigma, is measuring sizes. So this pi2, you take a generator, you take an element therein, represented by a disk, right? You have a disk in M with boundary on L. And you just measure its size. And size, of course, the only way to measure size is the symplectic form. You just integrate your symplectic form over the representing disk, and it does not depend on which disk you take because of the Lagrangian boundary condition. The difference is something you can see it in the Lagrangian like a cylinder, and the omega integral would vanish. So this is well defined. This is the area class with real values. And the second homomorphism is the Maslov class, the Maslov index. I not even define it. You should go into the Grassmannian and then look at the Lagrangian, the Grassmannian in the total thing, and then look at the loop induced, and then take somehow the element in pi1 there. And you can look it up if you want, but intuitively, it just means the following. When you have your Lagrangian, you you take the tangent bundle and trivialize it over the disk, and then you look how much the Lagrangian part twists when you go along the boundary, how much it rotates. I'm not precise. I will give you an example. You take a circle in C, and then of course you trivialize the symplectic planes along the boundary, just trivial, just like this. And then you look at the Lagrangian plane, which, well, when you have the circle, oh, you don't see me. Well, sorry, I cannot paint. Of course, it turns twice around, right? So the Maslov index of a circle in the plane is 2, because it's the non-oriented thing. It goes twice around. When you do a half turn, the tangent line goes around once, and then you close up, so 2. So this kind of is something like a winding number for the Lagrangian measured along disks that you trivialize and look at the boundary. So I don't want to be precise here. But monotone means that these two things, namely the area in the sense of omega and the twisting of the Lagrangian along circles that are boundary of disks, are proportional. So, and as you see by examples, this proportionality always induces some balancing and some symmetry. In the example of the product of circles, it's clear. And when you, for instance, take a circle in S2, then it must be really like an equator. It imposes symmetry. We will see examples. So technically, monotone just means that the Lagrangian is monotone if these two classes, the area class and the Maslov class, are globally proportional. The constant does not depend on A, but only on L and M. And it somehow means that there is a harmony between the omega size and the twisting along L. Okay, good. So now, so tori we have now seen many, and they are relevant in dynamics and when you have moment maps in toric geometry, you always have lots of tori. And then an important question was whether these classical tori are essentially all, or whether you can find other tori. For instance, in this Arnold-Liouville theorem, first, this was a very local statement. And if that torus you find, whether it's a usual torus, like a product torus, or whether it's something exotic, was not known for a long time. And already in R2N, this was open until 96, and then Chekhanov constructed exotic tori. So he gave a somewhat different construction. Now I will repeat the easiest one you can invent. It was done for the case k equal to 2 that I will give now by Eliashberg and Polterovich shortly later, and then I generalized a bit with Jura. So this construction is like this. Okay, so I repeat, we now construct in R2N and in other manifolds exotic tori, and they will be monotone. Otherwise, they would not be exotic. So exotic things appear essentially only in the monotone case, because they are distinguished from non-exotic things by holomorphic curves and Floer homology that roughly is efficient only in the monotone situation. It's not quite true, but approximately. Okay, so here is a construction. I want to give you one torus that you cannot immediately imagine that is still kind of visible. So you go to the plane and take such a sector. I mean that you divide the full 2 pi into k+1 pieces. And then in this piece of cake, you just smoothen the boundary by a curve that I fix to have area 1, but this is not important. So this red curve is gamma. And what is important is that it is in this sector that is given by the angle 2 pi over k+1. Okay, and now we will sweep this curve to create the torus. So I give you the answer, but it will, I will come back to it. So you sweep it, you take this gamma of t curve, and you act on it by a k torus. So they are k+1 variables, but there is a condition on the angles alpha I, namely their sum should vanish. Otherwise, it would not be Lagrangian. And then this scaling 1 over root k+1 is not important. It's only for later, for certain sizes. Okay, so this is the answer. This I call a twist torus. It's a k-dimensional torus in CK. Something is wrong. It's yeah. Okay, where is it? It's in R2 k plus 2, and it's a k plus 1 dimensional torus. Right. The notation is questionable. I call it theta k. It's a twist torus. So I will now. This is just a set, and I will describe it once more, and then it's probably clear that it is a Lagrangian torus, and also monotonicity will be quite easy. So let's do it again. So we take this curve as before, right, in this sector. And then we take the same curve, but we don't view it in a C or in an R2, but we view it in the complete diagonal of CK plus 1. So we take the set, the complete diagonal, Z. It's a copy of C or R2. And therein, I take this curve gamma of t, gamma of t, gamma of t with some scaling that you should forget. So now on this curve, the k plus 1 torus acts in the usual way, right? And therein, you take a certain subtorus given by the condition that the alpha I should match up to 0. And now when you take the orbit of this subtorus on this previous curve viewed in the total diagonal, you get exactly the thing before. So now you see this action is isotropic, and therefore it's clear that this thing is Lagrangian. It's also clear that it is a torus because the gamma delta was a loop, and then you have more loops, and then you act by this torus. So it's obviously a torus, right? And then this monotone is also not hard to check. There is only one. There are obvious generators. The gamma curve, and there the proportionality between area and index, well, is as it is, depends on the size. And then there are the other ones coming from this EI alpha 1 that you apply and so on, but they have Maslow's 0. So there is nothing to check, and therefore this is a monotone Lagrangian torus. It's a kind of an exercise. Okay, so these tori, they are really different. They live in, I have written CK or CK plus 1 because you can iterate the construction and you can take products to be somewhere in a Cn. But all of these tori are different from product tori, and you get in this way many different ones in some Cn, non-standard tori. I call them twist tori or exotic tori. So maybe I repeat the theta 5. When you intersect it with the complete diagonal, then it looks like this rosette, and you have these 6 pieces. And this condition that you are there was important to have it embedded. If the curve would have gone out of the sector, then the result when you act with this TK would actually only be immersed. So you have here some condition. And maybe the most important example is really when k is just 1. So essentially you take a half disk, you smoothen it, and you sweep it. So in the sequel, I will only work with this easiest example here.
Excuse
Fine.
me, Felix, how do you prove that they are all different?
Well, there I will explain it for this easiest example. There are essentially 2 methods, holomorphic disks and versatile deformations, and I will spend about 20 minutes on this. So I know 2 methods, and I like one of them better than the other, but we'll see. Thanks for the question. Other questions? So you need tools. You need really symplectic topology tools, but some of them are not so high-tech.
Sorry, Felix, can you maybe again explain how, from this picture, how to visualize this torus, the exotic torus? So how can we think, what is the lifting? Yeah,
well, in R4, well, you have this, you put it in a complete diagonal, and it's just what it is. It's e to the I alpha gamma of t, comma e to the minus I alpha gamma of t, where t runs through this gamma curve. So that's it. Mm-hmm. Yeah. Now visualize, yeah, I don't know. So, but I can tell you something. When you take the first Vienna torus, it's this one, up to a Hamiltonian isotopy. So if you can visualize the first Vienna, you are happy. But as I said, it's very different, but they are Hamiltonian isotopic. Then Oru has this vibration picture by, yeah, you take, you know, xy equals 0, and then you resolve it a bit, and then you have a monodromy. So this is yet another picture. Maybe you like that better in the Lefschetz vibration.
No, but I think from the toric geometry, it is a different one. So for example, what you say that if we construct it in different way, how to see that they are the same? How those other constructions which you mentioned.
So that this one is like the first Vienna, and that it is also the one of Oru. It's nowhere written because it's really not so easy. But you could go. So there is a third and a fourth description of the same thing. And when you compose 3 different Hamiltonian isotopies, you see that they are the same. I cannot visualize this isotopy. So that they are the same, everybody believed, because, you know, they have the same displacement energy, the same behavior of neighbors of displacement energies, they have the same canonical generators with the Maslov, so everything agrees. But to go from this description, for instance, directly to Vienna, I cannot see directly. I think nobody probably, maybe Vienna does, but I doubt it.
But maybe still about the visualization. Why it's only a half plane? So in the last picture, why you take only in the right half plane this circle?
This one, yeah, because I sweep it with this theta. So when you write E I alpha gamma of t, comma E minus I alpha gamma of t, if this curve would go to the other side, then it would not be embedded. It would be only immersed. Because you turn through.
Can you explain the sweeping again? I'm sorry, still.
Maybe I will write this down again later. So maybe specialize this formula to k equal to 1. So you just get this factor that you 1 over root 2 that you should forget, and you get e to the I alpha gamma of t, e to the minus I alpha gamma of t, where alpha runs through the circle. But the gamma of t is in the total diagonal. For me, this is somehow the best description. But for other things, of course, Vienna description is maybe better when you want to go on and produce infinitely many. And the Lefschetz description certainly has its merits too, to see the holomorphic curves. We computed the holomorphic curves from this description first. But the going forth and back between descriptions, there are papers about that solve this in some cases. Later we will put them into like S2 cross S2 and CP2, and then for each space there is a new description, because sometimes you don't have the space you want to have to do the isotopy. And yeah, maybe I don't know it well enough, but my impression is that this is not easy to see, that you always describe the same thing again and again.
Thank you.
Well, sorry, not a very good answer. But okay, I think it's relatively easy. You have this curve, this red curve, and you act with it by a circle. But things are kind of twisted because of this I alpha minus I alpha. So it's not a product torus. Also, the thing starts in the diagonal, not in a C-plane. Okay, so what I already said is that when you take such a CK, you can take products, or in a way, you see, we produce such a theta torus by twisting a circle. And you can also twist such a torus again, so you can do higher twisting. And then you get many other examples. And the full enumeration is kind of not fully worked out, only partially, but it lost some interest because in a given Cn, you only get finitely many in this way. And Oru then produced in R6 and bigger, infinitely many different, up to symplectomorphism, monotone Lagrangian tori. And their precise relation to what you get, you see, we have now here infinitely many, and we produce with the old description something like in R14, we produce something like 2 to the 14. So how they intersect with the Oru family is unknown. Also in R4, only 2 are known. Only the product torus and the first Cherenkov torus, and nothing else. Okay, however, in CP2 and in S2 cross S2, infinitely many are known by this famous Vienna construction with nodal slides, and I will not come to it, but this is a different construction and needs almost toric vibrations and is a kind of very attractive. But sorry, I have just no time to explain that. So this works very well in products of spheres and more generally products of CPN, and essentially in, well, Vienna construction works in all the Bezier surfaces, and other constructions work in all monotone toric symplectic manifolds. I don't want to be precise. It's a kind of a wild zoo, and it's ongoing research and many open ends. Okay, so the last example, of course, I should really not forget is the origin from algebraic geometry that you probably all know much better. You take a polynomial on Cn with complex coefficients, and then you take the zero set. You get an algebraic variety, and I want it to be smooth, and then this will be, this Vp will then be my symplectic manifold, right? This will be M. So now, and this is a Kähler thing, because the usual symplectic form omega 0 on Cn restricts, because of it's a complex polynomial, it's a Kähler manifold, right? Good. So now I specialize, and I assume that these Aj, the coefficients, are real. So now when you take the usual complex conjugation involution on Cn, then you can restrict it to Vp, because you'll see it when this, do you see this blue? Did I make it blue? Oh, this may be useful.
Yes,
when you
yeah,
look at this, of course, the conjugation, when it was 0 and you conjugate, because the Aj are real, it will still be 0, right? Good. So now you have a symplectic, not a symplectic, an anti-symplectic involution that I called here sigma Vp. The restriction is a typo, should be restriction, that maps Vp to itself. And this is not quite symplectic, but it changes the sign because there was the bar, right? And because of this, the fixed point set of this involution is, what do I want to say? Well, first of all, it's a real algebraic variety, and it is actually, when you assume that Vp is smooth, it's automatically a submanifold and automatically Lagrangian. So now we have many examples. So in the algebraic geometry setting, the Vp may be not smooth, but once it's smooth, the smoothness of the fixed point set of the involution is automatically smooth, right? For a smooth involution, the fixed point set is always a manifold. And it is Lagrangian because of this sigma pullback switching the sign. Follows immediately. So in this way, you get many special Lagrangian submanifolds in algebraic varieties. So this story is, of course, very famous, right? By the way, maybe you don't like this in Cn because it may not be compact. But then when you want to make it compact, you just start in CPN and do exactly the same thing with homogeneous polynomials P, right? And this is, of course, in your place, probably still a big story, because Rohlin really initiated the question which topological types you can realize by in this way as real algebraic varieties. And now, of course, they were then, he initiated it and had many results, and there are books by Dektyarev, Kharlamov, and Dietenberg and Grisha have done much work, and also Salman and many other people. And this is a big field. So in this algebraic geometry setting, the involution in question, as far as I understand, is always something really canonical, like Z goes to Z bar. So the mapping is kind of given, and then you ask which topological types you can realize in this way. And then in a way, you also want to classify them up to this Z bar in an equivariant way. And there are some different kind of classification, and I'm not quite sure which ones are really different and which ones are important. But now from a symplectic point of view, this very special map, Z goes to Z bar, is not natural. any symplectomorphism that would switch the sign of omega would be natural, and you would look at the fixed point set, and you again get a Lagrangian, and such a thing you would call a real Lagrangian. So from a symplectic point of view, you take this as a paradigm and as a very important historical thing, and make the following generalization. You say that a Lagrangian in a symplectic manifold is real if you can find an involution that is anti-symplectic and has that thing as the fixed point set. This is more general, and so the big question is whether the results proven by this school in the algebraic geometric setting survive under this more general symplectic setting, which looks more flexible. And if so, what are the reasons? You see, if the result survives, then it's in a way remarkable because something is much more rigid maybe than expected. And if not, then you know that what you have proven in the algebraic geometry world was really depending on the integrable structure and the special involution. So these questions are relatively fresh, and there are some results, and it's not so clear how far one can go. Okay, so for the rest of the talk, I will speak about real Lagrangians. So I will take Lagrangian submanifolds, and I will ask myself whether they are the fixed point set of an anti-symplectic involution or not. So by the way, in this definition, there is a choice. So here I can either write equal or I can write a component of, right? And this is a matter of taste. And for the results proven up to now, it doesn't really play a role, but one should be careful whether one wants to have exactly that Lagrangian, which I assume usually connected as the fixed point set, or whether you just want to have it included as a component. Okay, so now I will do the obvious game. I will repeat all the examples I have done, and I try to find out whether they are real or not. So real now means that you have to invent a symplectomorphism that fixes that thing, right? The symplectomorphism is not given, like Z goes to Z bar. It's anything, and you want to see whether it works. Okay, let's start. It will be very easy, so I go a bit fast. When you take a closed curve, obviously it doesn't work because the interior should go to the exterior, but one is bounded, one is unbounded, but this area is preserved, so it cannot work. It could also be seen for topological reasons, but okay, so the first example fails. But when you would put this curve in a monotone way into the sphere, then it of course works. You just flip, right? Z goes to minus Z. So here we have an example. So now let's go to these dynamically important things. So they are all real. I just give you the answer. You take for the graph alpha of Q, you just first map it down to the zero section, then you map QP to Q minus P, and then you conjugate back, and the outcome is this formula. So this works, and this is symplectomorphism. And these fibers, you can also include them by just taking any diffeomorphism of the base that fixes the base point. Good. So these graphs, yeah, they also work. So such a Lagrangian graph, it's just a fixed point set of what I wrote down. You first do it with phi equal to identity. Then it's just swapping x, y goes to y, x. And if you have a graph, non-trivial graph, you should fiddle with phi. And you check that this is an involution, it's symplectic, and it fixes exactly gamma phi. So they are all real. Okay, so then you go on for a while, and then of course you go for the algebraic geometry. This is real by definition. So you have the impression that real is kind of generic, that it is kind of not very special because you have so much flexibility on the phi. But then, so newer work shows that for instance, in the torus fibers, in particular in the moment map situation, then reality is very rare and very, very special. So this first impression in the dynamical examples is just not true. When you go for the toric picture, and I will come back to that, then you have to prove something. Reality is very rare. Okay. So then the generalization of the circle in the plane is these tori. Yeah, they are also not real. And this, you see, this is very easy to see because when you do, I mean, you know that, when you do symplectic geometry and topology, and you prove that something does not work, you can make a fool of yourself by using Floer homology and holomorphic disks. You should really first check that it is not a smooth phenomenon. And sometimes the fact that a manifold is not real is just for smooth topology reasons. So when you prove something, you should first check that the smooth obstructions are all zero, because you can move smoothly, or you can do it by a smooth involution, but not so antisymplectically. And I just briefly recall this. So it is actually very beautiful. It is called Smith inequalities. You probably may know that. So here I take a smooth manifold M, just a smooth manifold, doesn't need to be closed. And then I take a smooth involution, and I assume that the fixed point set is compact. So then the topology of the fixed point set, that is a smooth compact manifold, is actually quite tightly constrained by the exterior manifold M. The Euler characteristic must have the same parity, and the total Betti number cannot exceed. So the total Betti number, let's do over say 2, cannot be bigger than the one of the ambient manifold. And this oftentimes gives you restrictions. Now let's do it immediately. A torus in R2n, well, the Euler characteristic of the torus is 0, but the one of R2n is 1. So already the first Smith inequality says no. And the second even more, because the total topology of Rn is only 1, but in the torus is 2 to the n. It's enormously wrong, right? Okay, so I mentioned this because in the topology books, these Smith inequalities are not so easy to read. The first one is, of course, very easy. You just take a sigma invariant triangulation or a sigma invariant CW structure, and then you count cells and remember that the Euler characteristic can be read at the chain level, and then it's there, right? You triangulate the fixed point set and extend that triangulation invariantly, and then those not in L, they are matched by sigma, so mod 2 it cancels. So this proves 1. But I think the topological proof of 2 is not so easy. Well, it's something like 2 pages in Prud'homme book, but not so easy. But when you know what, I cannot repeat what it is, Morse homology, but when you know Morse homology, then 2 is actually a very simple, obvious exercise. So sometimes Morse homology that led to Floer homology is really very nice to see the cell proofs of topologies in a different way. But maybe, Grisha, you can also prove 2 in one shot. I don't know. But for me, when you know Morse homology, you prove 2 and you find it wonderful. Okay, so these are the Smith inequalities, and they exclude many things. For instance, I just do some examples. When you take R2n, of course, both inequalities exclude tori. When you go to CP2, both of them exclude tori, because in CP2, Euler characteristic is 1. Well, it's probably 3, but it's odd and tori are even, and also the other one fails. But in S2 cross S2, neither 1 nor 2 works, and the reason is that you have tori, product of equators, right? They are real Lagrangian tori. You in this first, you have these 2 spheres, you take the 2 equators, you flip on both sides, of course they are real, right? Okay, so I wanted to repeat that because it's important that you look at the examples where smoothly there is nothing to see. Okay, and the last point is of course also always real by definition. We started from there, right? Great. So now I ask a harder question. I ask, these twist tori, are they real or not? Well, in R2n, we cannot ask a question because we have just seen that smoothly there is nothing to see. But now I put them into S2 cross S2, and I will not give you the details. But the construction, I repeat the construction. You take this circle and you are a bit stingy with sizes, because when you do it then it does fit in S2 cross S2. Just think of S2 cross S2 as compactification of disk cross disk in C cross C, and then this torus we constructed, the theta, fits in a monotone way, direct computation. Okay, so we have it there, and now we can ask, is it real or not? And this is not so easy. So the answer is it's not real, and I want to show you two proofs. So the first method is probably the one all hardcore symplectic geometers prefer. So it comes from holomorphic disks. So already before we have seen disks to define the Maslov class, but now we take special disks, we take holomorphic disks, because rigidity is usually there. So you take on your symplectic manifold, you cannot take a complex structure because it may not exist, and also certain things may not be generic. So you take an almost complex structure, but you take it, as Kromov did, you take it so-called compatible. You take it such that, like in the Keller situation, when you pair it with J, you get a Riemannian metric. And you can always do that, and there are many such J, and they form a contractible space, a big non-empty contractible space. And then for such a J, you look at what you think to be a holomorphic map from the disk to the manifold. You take the usual disk, so this thing is the usual disk of radius 1 in the complex plane, and you map it smoothly to M such that the boundary goes to the Lagrangian, and such that if M were Cn, you are exactly holomorphic, Cauchy-Riemann equation. But you now write it in this almost complex manifold, so you want to satisfy the somewhat generalized Cauchy-Riemann equation, right? And here, this golden thing, it's so precious that I write it golden. This is a picture of such a disk, okay? Lagrangian boundary condition. So now you would like to say, I count these disks, and then I get an invariant. So this can only be done in a, you see, it should not depend. When you count, you should first say that you want to go through a fixed point in the Lagrangian. Otherwise, you have too many. Second, you want to have the thing independent of J. Otherwise, it's not a good invariant. It should depend only on L and M and omega. So this only works when you say that the Maslov index of the curve is 2, because then something bad cannot happen. There will be no bubbling. So the number, the count of disks of Maslov index 2 that are holomorphic for a generic J, there is something to say, through a given maybe generic point, this is what we take as our invariant. The mu2 is the Maslov 2-disk count through a generic point. And then Kim proved that always when you are real, this count is even. And it's not surprising, but it needs a proof. I give you the idea, and then you say it's obvious. So you take your golden thing, and you have already a sigma. So because you are real, you have your involution. I didn't write it down. So this involution will make from your golden object another one. So you have to check something. This count is up to reparametrization in the domain. So what you have to check is that the golden thing is not equal to the blue one. So you see, of course, the golden thing is not in the Lagrangian because it's a holomorphic curve. So the omega area is not 0, but it could be that it's kind of like in a yin-yang, that it goes out and then goes to the other side, the disk, and the involution maps it to itself. So you have to exclude this. And this needs a little argument. This needs an argument. And the proof in dimension 4 is easier than in higher dimensions. I guess this was kind of known to specialists, but it is good that everything is worked out, and it's kind of nice to know. So if you want to be real, your Maslov 2 count must be even. So for theta, we have checked some time ago with Juracekhanov that there are 5 disks. So it means this theta guy is not real. Okay, so this is a good method, this mu2. And of course, everybody in, well, like in Fukaya category working and so on, they will be very much interested in this method if they are interested at all in real Lagrangians, because the Maslov 2 count is very important for other reasons. But it is not easy. So you can do it in some cases, but in general, counting disks is an industry, and Grisha is a specialist, and I hope you agree that you can do it in toric situations oftentimes, and in general, it's rather hopeless. For toric fibers, it's not so hard maybe, but these theta guys, they are not toric fibers. So for the higher theta tori, for the higher twists, we don't have a general recipe how to compute oh sorry, mu should be mu2. How to compute the number of disks. Okay, so in general this is hard, and therefore I now outline in my last 5 minutes an easier method that was used by Schlenk to prove the same result and many others that exclude reality. So this method is, I like it very much because it's very elementary, and people seem not to use it so much, so I'm happy to explain it again. It is about versatile deformations. So the idea is that this was introduced by Chekhanov to distinguish the split torus, the usual product torus in R4, for instance, with his first twist torus. And the same method as Brendel observed and also tells you that a certain function must be even if you want your Lagrangian to be real. So I just repeat how it goes. So the idea is that these monotone Lagrangian tori, they usually have symplectic invariants that are not very useful. Certain are infinity, and certain are certain are very hard to compute, and others are always 2, like the minimal Maslov, and so on. So the idea of Chekhanov is to compute invariants not at the Lagrangian, like we did before, the J-disk count, but at the neighbors, at nearby Lagrangians. But you want, of course, there's an infinite dimensional Frechet manifold, the nearby Lagrangians. So you want to only pick in every homology class, like in the Weinstein neighborhood, for every homology class in the Weinstein neighborhood, one Lagrangian, and on that element of the homology class, you want to assign a value and thereby get a function, and this function should kind of say something about the central Lagrangian you have in mind. So I just give you an example. You choose your preferred symplectic invariant. For us, it's displacement energy. It is kind of how heavy the manifold is. It is the energy you need to move in a Hamiltonian way the Lagrangian away from itself. So I repeat, for any subset of your manifold, later it will be certain Lagrangian tori, you define the energy as follows. So what is this thing? It's called Hofer norm, but what it is, if the Hamiltonian does not depend on T, it's just the oscillation, just a C0 norm. But if you are non-autonomous, you should take the average of the C0 norms of the Hamiltonian, right? So I assume M compact, or at least H compact is supported. So you take any Hamiltonian, and then you take all Hamiltonians in the world that move the set away from itself in time 1. You want to disjoin it. If it doesn't work, this norm is infinite. If it works, it's a real positive non-negative number. And then you take the easiest way to do it. So it's an optimal transport problem in a Hamiltonian setting, right? You have your subset A, and you try to move it away, and you measure the minimal energy that you need to do that. So to understand this, you should do one exercise. You should check that for the disk of area A in the plane, the outcome is the area. It's a very important exercise when you want to work with this. But okay, good for this too. So now this invariant for our tori, because they are monotone, like in S2 cross S2, is quite useless because they are non-displaceable. It's infinite. But the idea is to compute it on neighbors on this green patch. Because locally, the Lagrangian tori up to, you want to have something finite, up to Hamiltonian isotopy, is just H1. Locally, it's at the level of germs, right? A neighborhood in H1 is exactly the set of nearby Lagrangian tori up to local Hamiltonian isotopy. So this is exactly the content of Weinstein. Usually it's not said this way, but his proof gives exactly this. So the neighbors of our L we want to understand, I shouldn't have used L, the L primes, near our L can be identified locally with the first cohomology. And now such a symplectic invariant like E, of course, descends. So it's an invariant for any Lagrangian, let's say torus. And because it's a Hamiltonian even symplectic invariant, it descends to this quotient and therefore gives a mapping term, gives a map on H1, at least a neighborhood of the 0 point in H1. For tori, it's just an Rn, right? And it may be infinite. At 0, it's infinite in the monotone case oftentimes. But it's a function. And this function term is an invariant. For instance, we will see that for the product torus in S2 cross S2 and for the twist torus, these two functions are very different. And therefore, these tori are different. So what Brendel proved is that if L is real, this function, which is a function on the vector space, H1, must be an even function. E of P must be E of minus P. And once you observe it, the proof is not very different. A bit of equivariant symplectic topology and the observation that if you can displace by a Hamiltonian a set, then you see the problem is if you precompose H with sigma, yeah, this is not, E is a symplectic invariant, not an anti-symplectic invariant. But the minus sign you have to plug in doesn't matter because in the Hofer norm you have absolute signs. So then you conclude immediately that the displacement energy of sigma of a set does not change. Okay, and from this, with some fiddling and equivariant Weinstein neighborhood and being lucky, and you get the theorem that the function must be even. Okay, and then what Brendel also does, he computes for many twist tori and exotic tori this functional. And for instance, for theta and S2 cross S2, for this first twist torus that we plugged in, the level sets of the function are triangles. This is not even. So theta is not real. And this method applies in many, many ways. So for instance, it works for central fibers in monotone toric symplectic manifolds. Well, here you can indeed, as Krisha pointed out, also work with J-disks, works also. And in general, we do have the impression that these versatile deformations give you essentially the same information as J-disks, but the precise bijection is not understood. For twist tori that are not toric fibers, the J-disks are really much harder to compute, I think. But this method of versatile deformations works many times. And for instance, an important point is that you can do, like in a Dale sound construction, you can always go back to CN. And the only hard symplectic tool you need is to know what the displacement energy of a split of a product torus is. And this identity that it's just the minimal one that is obviously a candidate, but then you have to show you cannot do better, just moving the smallest disk, that this is the answer. This was proven in a very early time of capacity theory, 95, by Hofer and Zickeraf. So this uses only kind of linking in loop spaces in linear space. This is much easier than J-disks. Okay, I think I'm done. Great, time is over. Thanks for attention.
Okay, let's clap. I have probably a stupid question. So,
Great.
is it true that all real Lagrangians are monotone?
Yeah, it's a very good question. So when the manifold is so how is that? I probably do it wrong. When the manifold is how is it? Show it.
The ambient manifold, I guess, must be monotone. Yeah.
The ambient must be monotone. Otherwise, you cannot be real because the sigma gives you immediately a proportionality, right? Right. So to ask to be real only makes sense in mono. You see, I didn't want to introduce too many notions, so I've introduced monotonicity for the Lagrangian, but there is also monotonicity for M. There it means that the first Chern class is positively proportional to the area class on spheres, on pi2, on absolute pi2. So if L wants to be monotone, the ambient manifold has to be monotone, and to be real, it has to be so. Right. So there is a global restriction already.
So questions, comments? Everybody are welcome. Oh, Grisha wants to ask some question. Yeah, please raise your hand to just unmute your microphones. So Grisha, please.
Okay, so my question is about the displacement energy. So is it true that this displacement energy has a bound from below by the smallest disk?
That's true. That's Chekhanov theorem, and I did not want to mention it because here it's not used. That proof is really high tech and very beautiful because it needs kind of Floer homology, but then it is not. You see, Floer homology at least 10 years ago was only established in monotone manifolds because otherwise you get a mess with bubbling. But Chekhanov proof is such that exactly bubbling cannot happen because your size is below. So the inequality that Grisha mentions is the following. You look at all, for a generic J, you look at all holomorphic disks that are non-constant with boundary on the manifold. Then for every J, you take the area smallest disk, and then you take the supremum over all J, because for a fixed J, this size is a lower bound for displacement energy. Since it's true for every J, you can take the sup. And this number is a lower bound. And in all examples, I know it's actually sharp.
Say it again, so it's sup over all possible J structures?
It's sup over J of min. I say min because Gromov compactness say, okay, it's sup J inf area of size of J disks. And inf is min because of Gromov compactness. So if you fix J, you do find a disk that attains the minimum, and then you supramize over all J's.
But initially I was, in the case, if our manifolds are, in this definition of Hofer norm of both subsets are Lagrangian, then I meant maybe a simpler thing that even the Hofer norm, right, I guess should be bounded by below by the smallest area of some disk, not necessarily holomorphic disk, let's say just say symplectic manifold without.
You mean the Hofer norm of a Hamiltonian that displays this Lagrangian?
Right. Yeah, because it's one like now I'm confused. So the definition, so it's still displacement energy, right? We need a Lagrangian and we need a way to.
L is fixed. I don't move from L to L prime. I take L and want to disjoin it from itself.
I see. And if we don't if we don't worry about the J disk, but want to take a minimum over all possible disks, would it be an easier theorem that say we don't care about the complex structure, but just to have a minimal? Right. But then it's, yes.
So I think it
it doesn't make sense. Yeah. Okay. So
I think it gives nothing.
We need to do it like this. Yes. Okay. Sorry. Okay. Thank you.
Now, thanks for the question. So these things can be. You don't have to do this lifting to Cn, but since the target manifolds in all these results are toric, you go to the universe, you go to Cn, you lift also your Lagrangian. So of course there is much work to do. You have to in this business, you have to you really have to compute E. It's not enough to have estimates. So you need lower bound and upper bound. So interestingly, what Rehnl did is that the lower bound he get by symplectic reduction downwards and the upper bound by lifting and seeing what you have as symplectic reduction of the Cn business. So it's kind of always the same method and it's only symplectic reduction. So it's very elementary in a way. Up to this result, but to this we are very much used because the Grant-Hofer capacities and the several capacities are done by a certain linking in an infinite dimensional loop space, but you only have to do some Fourier series stuff. So this equality can be really, you can do lectures on that in the third year, maybe. But J-disks are, of course, extremely important because they are connected to other things. It's a bit of a matter of taste. The second proof, I like the thing because they apply both to say that theta is not real, but they apply in a way in different directions to prove non-reality.
Okay, more questions? Misha Polek collapsed. Probably Misha Polek wants to ask a question.
Misha, you're great. You're here.
Hi, Misha. Oh, Selman writes that is good lecture.
Thanks, Al.
I think so. Yeah.
Yeah, try. I learned from Dusa McDuff that the easier you are, the more successful.
Yeah, I like it very much. Yes, I also understand almost everything. It's rare.
I'm still confused.
Like real Lagrangians. No, sorry to be so basic. Now, for us, it's impressive. Whatever can be proven with these versal things, well, a year later, you see a paper from Fukaya people. And they are really fabulously strong, but I cannot understand, right? So, yeah. It's a matter of taste, which method you like better.
Okay, more questions? Then let's thank speaker again.
Thanks for your attention.
I stop recording.